This is part 4 of our study of electrochemistry. In our last video, we looked at the Nernst equation where we're calculating delta G for standard conditions. So standard potentials do assume concentrations, remember, are 1 molar. That's something we learned in our thermodynamics unit. This form of the Nernst equation that we're fixing to look at allows us to calculate the cell potential and the delta G, the free energy, when the two cells are not at 1 molar, so they're at non-standard conditions. So E, again, your cell potential, would be equal to the standard cell potential, so you would calculate the standard cell potential, minus RT divided by NF, and then that's times the natural log of Q again. So let's clarify what each of these symbols represents. R is your 8.3145 joule per Kelvin mole. And for the most part, you can just say 8.31, but the entire value is 8.3145 joule per Kelvin mole. The temperature does need to be in Kelvin to cancel with the Kelvin we see here. N is the moles of electrons in the balanced redox reaction. F, again, is Faraday's constant, 96,485 coulomb per mole of electrons. And then Q is, again, our reaction quotient, which is the products, concentration of the products divided by the concentration of the reactants. We will be using this formula in class as we do some guided practice. Now, at 25 degrees Celsius, the Nernst equation can be written or simplified to this form. The cell potential will be equal to the standard cell potential minus 0.0591 over N. So what we've done here is we've taken into account what the RT and the Faraday constant would equal. That would give you 0.0591 over N times the natural log of Q. At equilibrium, the forward and the reverse reactions occur at equal rates. Remember that from our equilibrium chapters that we studied, chapter 15, 16, and 17. So at equilibrium, what happens is the battery is what we call a dead battery. Whenever the reaction reaches equilibrium, the battery is considered dead and the electrons no longer flow. So at this point, the cell potential is 0 volts. If we modify the Nernst equation at 25 degrees Celsius and plug in 0 volts for our cell potential, assuming the battery is dead or has reached equilibrium, plugging into the Nernst equation and solving, the standard cell potential would have been 1.10 volts when the battery was working at standard conditions. 0 volts is when it's when it is at equilibrium. We had 2 moles of electrons, and that's times the log of K. If you solve for that, you can get your equilibrium constant K. So for this one, you got 1.58 times 10 to the 37th power. We will be in class going through some of the calculations using those formulas, so don't worry. Don't be overwhelmed. We will definitely do some in class. All right, the next slide here talks about the electrolytic cell process. Remember, this was your second type of electrochemical cell, an electrolytic cell. These have non-spontaneous redox reactions occurring in them. So the energy that is produced in an electrolytic cell is produced by an external power source that causes the non-spontaneous redox reaction to occur. Notice here, instead of having a light bulb hooked up, we have a voltmeter hooked up. These have a negative cell potential because they're non-spontaneous. So they have to be sort of jump-started with an outside power source. Since they have a negative cell potential and they're non-spontaneous, that means if you were to calculate the delta G, it would be a positive delta G. Again, non-spontaneous. Notice here, I've got the copper electrode on this side and the zinc electrode over here. So the electrons are not going to flow as they did in the galvanic cell. One of the little videos we looked at was looking at how the copper metal plated out in that zinc copper electrode. Well, you know, many of you are very familiar or you've heard of like electroplated metals. Like you can have silver plated or gold plated jewelry that has like a cheaper metal underneath, but they've plated out the gold or the silver on top of it. They actually use electrochemistry to do the electroplating. This is a picture of a little electrolytic cell. Notice they've got a piece of silver electrode here, and this is just a spoon, an iron spoon that they've put in, another kind of a cheap metal. They have it hooked to a battery, of course, and as the electrons flow, the charge builds up on the metal, and so that allows the silver ions, which are cations, to migrate towards the negative charge on the metal that was placed in the electrolytic cell. And so the silver plates out on the spoon, and you have a silver plated spoon. Now the anode in this reaction is silver, forming the silver ion plus electrons, and the cathode is silver plus electrons yield silver. The electroplating requirements that must be met here. The solution that's present has to be the solution that contains the ion of the plating metal, like whatever metal ion you want to plate onto the cheaper metal. The anode is made of the plating metal. So our anode is made of the silver, made of the plating metal. The cathode is the object that we want to be plated. It can be any other like type of metal that you have. In this case, we have an iron spoon. And the fourth thing you need is a source of current. That's your power source, because remember, these are non-spontaneous reactions and they have to be powered by an outside source. We'll look at that a little bit more in class. All right, the last slide here is on how do you solve an electroplating problem. So here's a typical example. It says, how many seconds will it take to plate out 5.0 grams of silver from a solution of silver nitrate if we use a 20 amp current? So here's the reaction. It's plating out silver from silver nitrate. So you want to write the redox reaction here. Silver yields silver ion plus electrons. This is your oxidation half reaction, is losing electrons. So you would start with your 5 grams of the silver. So this is silver, the metal. So you're going to need the molar mass, or atomic mass in this case, of silver to get your grams to cancel out. You see there's 1 mole of electrons that's involved here. So it's a 1 mole of silver to 1 mole of electrons, your mole ratio. That's going to let your moles of silver cancel. And now we're going to use the relationship, which is Faraday's constant. 96,485 coulombs is equal to 1 mole of electrons. So this lets moles of electrons cancel. Now, if we stopped here, our answer would be in coulombs. But this wants to know how long. Like, we want to know how long is it going to take us to plate 5 grams of silver onto our substance we're trying to plate it onto. So here, you are given here that we have 1 second, you have 20.0 coulombs. Okay, because here's your 20 amp current. Okay, that's going to let coulombs cancel out here. And so that leaves you with seconds for your final answer. All right, so when you plug all that in using the stoichiometry, you do get 2.2 times 10 to the second seconds. You could convert that to minutes if you wanted to. That would